Hi guys, you are welcome once again to the Smart Way lectures on the Science Ambassador series. This is a series of lectures we are running on all the areas in science, and today we are here with you to continue on thermochemistry. In our last lectures, we look at the energy diagram involving in exothermic reactions. We have explained that exothermic reactions are reactions that liberate or produce or give off heat to the surrounding. The surrounding in this case tend to what? To increase in temperature. So if you are using thermometer to measure the reaction, you realize that the temperature of the thermometer will rise up because the surrounding has increased in in heat or energy level. And so, but the reaction itself will end with a lower heat content, but the surrounding will increase in energy. We gave you example like the combustion reaction, like the burning of the paper. Okay, such reactions always give off heat to the surrounding. And so we're able to explain that. Today we are going to take you briefly through a typical examples with the one involving in bond breaking and bond formation, and how the reactions really occurs at the bond breaking level. Okay, so I'm going to do that very shortly, then I'll go to the endothermic reaction. So let's start. Now when you look at the energy diagram, as I said earlier, that before you start every reaction, there is a minimum amount of energy that you supply to the reaction. Before the start of every reaction, there is a minimum amount of energy to start the reaction. Just like we are burning the paper, you have to light the matches to make sure that the paper can catch up the light. So you add some energy to start the reaction, and so that energy, we said in our last video that it is what we call the activation energy. The minimum amount of energy given to a chemical species or a reactant to react to become the product is what we call the activation energy. So this from here to here is the amount of energy, from here to here is the amount of energy that you have to supply to the reactant in order to become the product. And so what is the reaction? What is this energy going to do? Now this is what it's going to do. So let me give you one practical example. Now assuming that we want to form water, in the formation of water, we know that it is hydrogen gas. The hydrogen gas are combined with the oxygen gas. Hydrogen gas are combined with the oxygen gas in order to form the water that we know. That is the liquid water that we know. So this is a reaction in the this is a exothermic reaction involved in the formation of water. This is a liquid. So that is it. Now in this reaction, before the oxygen and then the hydrogen combine together to form the water, you have to supply energy to the reaction. So this energy is called the activation energy. What is this energy going to do? The energy is going to break the bonds of the reactant. So the hydrogen HH bonds are going to be broken, and then the OO bonds are also going to be broken. They are held together, so they have to free them before they give you the product. So you supply energy to the reactant. The reactant absorbs energy, and the absorbed energy is used to break down the bond. Now where is the absorbed energy going? The absorbed energy at this point is going into the atoms. The atoms will take up this energy. The atoms will take up this supplied energy, and as a result, when the bond break, the individual atom that has gained this energy will increase in potential energy. So you can see that here there's a rise in energy. So this is now the free atom that has come out from the bond breaking process. Okay, so the bond breaking process, these are the free atoms that has come out from the bond breaking process, and so these free atoms will have to rearrange themselves in order to give you the product. These free atoms will have to rearrange themselves in order to give you the product. And so, but remember, they have higher energy because the energy that goes into the reactant used to overcome the bond goes into the atom. The atom acquired this energy and then raise their potential energy up. Now at this point in time, because the energy has risen, they are not stable at all. And so I told you that at this point there is what we call a transition state. At this point there's what we call a transition state. In the transition state, what basically happened that the atoms that has come out from the reactions are highly unstable. They are highly unstable. They are the ones that are combining and doing the rearrangement in order to give you the what? The product. And so I define the transition state as it is a highly unstable state of what? Of a reactant. A highly unstable state of a reactant that proceed to give you the what? The product, or even come back to form the what? The reactant. That proceed to form the product or come back to form the what? The reactant. Now, so that is what it is. So this, at this point in time, there is higher energy. These species are having high energy because, as I said, bond breaking has taken place, and the energy that is used to break the bond goes into the individual atoms, and so they rise in energy. They have to rearrange in order to give you the the product. Now, this rearrangement, as they are arranging themselves to form the product, something special also happen here. Now, as these atoms are combining to give you the product, from the transition state, they tend to lose the energy that was acquired in the first process. So they tend to lose the energy. So in the formation of the product, the highly energetic atoms, okay, the high energetic atoms lose their energy as they are combining and to give you the product. Now, at this point in time, you can see that in exothermic energy diagram, the energy that is liberated by these high energetic atoms, okay, the energy that is liberated by this high energetic atom are very, very, very high, and so this energy goes into the what? Into the surrounding. Okay, this energy is liberated. So this is the energy that is liberated to the surrounding as the individual atoms are combining, as the highly energetic atoms, or as the high energetic atoms are combining. They give off the energy to the surrounding, and they tend to have what? A lower what? Heat content. So you can see from here that this is the transition state of the water. At this point, real bonds are not formed. You see, so I have indicated by dotted lines that they are now trying to give you the what? The actual what? Water. That is this H2O. Okay, they are now trying to give you the A2O. And so I've used what's called a dotted line to indicate that they are not fully bonded to each other. But because they have high energy, they are arranging themselves, and as they are coming together, as these high energetic atoms are coming together, they are giving off this energy to the surrounding. And in exothermic reaction, the energy, okay, that is given off, okay, the energy that is liberated to the surrounding as a result of the combination of these atoms are higher than the energy that was absorbed by the reactant. They are higher than the energy that was absorbed by the reactant. In this case, you can see that the excess energy, okay, goes into the into the surrounding, and so the surrounding tends to increase in energy, or the reaction will give off energy, because why? During the bond formation, the high energetic atoms give off their energy and become very, very stable at the end of the day. So water here become very, very stable. Water become very, very, very stable compound, because during their formation, high amount of energy was given out at that energetic level. So that is what basically happens in the exothermic energy diagram. I wasn't able to explain this one, so I have now taken this on a detailed level so that you can understand what basically happened. Now, once again, in exothermic reaction, the energy that was supplied, the activation energy that was supplied to the reactant to break down the bonds is smaller than the energy that is released during the actual formation of the product. Because, as I said, when the energy goes inside the reactant, this energy is used to overcome the bond and goes into the individual atoms. These atoms rise the energy level. These atoms are free atoms now, separate atoms. But as they come together to give you the product, they give off energy. And in exothermic diagram, the bond formation, the process of the bond formation gives you higher amount of energy than the one that is used to break down the bonds. And so basically, the excess energy, the difference in energy, that is the difference in energy that is between this and this one, it will give you the negative value. And then we explained that in our last lecture. So when you subtract the energy level of the reactant, that is the enthalpy of the reactant are away from the enthalpy of the product, because the reactant is of higher energy value. So if I use this 15, if you consider here to be 15 and here to be 10, because the reactant is of higher energy value, you have negative 15, okay, minus what? Minus 10, and the result become negative. Okay, the result become negative. Remember, because energy was given to the surrounding during the bond formation, the product ends up to have a low heat content, okay, compared to the reactant. Now quickly let's move to the exothermic energy diagram. Okay, so in the endothermic energy diagram, or in the endothermic process, basically what happens is that the reaction rather takes or absorbs energy from the surrounding system. The reaction absorbs energy from the surrounding system, and as a result, it ends up with what? A higher heat content. I'm saying that in the endothermic process, the reaction rather absorbs energy from the surrounding system, and so it ends with a lower heat content. Now let me give you a typical example, like the one that I use, the heating of water. Okay, so let me give you a typical example like the heating of water. Good. Now suppose you have your water in a beaker that you are heating. Now with that you are heating, so this is the heat. Now you will see that at the beginning of the reaction, the water will have a lower heat content. Lower heat content. So at the beginning of the reaction, or before the heat, it will have a lower heat content. Okay. Now, but when you put the water on fire, after some time, you realize that the water will absorb energy from the surrounding. And at the end, the temperature of the water, if here it started with say 25 degrees Celsius, at the end of the heating process, you would see that the temperature of the water, the temperature of the water will rise, okay, and will move to around 100 degrees Celsius. That is during the boiling process. Have you gotten that? And so in this case, you can see that the reaction or this process has absorbed energy from the surrounding and has risen the temperature. So it ends up with a higher heat content. So the reaction ends up with higher energy, okay, content, okay. So higher energy, okay, or higher heat content. So this is what's called the exothermic reaction. In all exothermic reaction, energy is absorbed from the surrounding system, and if that happen, what basically happens that the surrounding sometimes become cold, okay, and then the system, okay, become very, very hot. So the product ends with the higher heat content. The product ends up with higher heat content, okay. So that's what we call the endothermic process. So in the endothermic process, once again, the energy is absorbed from the surrounding system, and it ends up with a higher heat content, okay. Now let's look at this example, okay, in this diagram. In this diagram, you can see that the reactant is having lower energy as compared to the product, because just as I said, the product at the end of the day will gain energy because it will absorb energy from the zero state, and then at the end of the day it will gain energy. So now the heated water will now have higher energy than the one you started with. So this is the explanation for the diagram. But let's take a typical example. Let me take you a typical example of a reaction, like the dissolution of this. Let me take a typical example like the dissolution of this particular salt, okay, ammonium chloride. Now anytime you dissolve ammonium chloride in water, it has been found that ammonium chloride is a solid. When you dissolve it in water, it has been found that the water ends, okay, or the water becomes very cold. So that means that if you have a beaker here and you put in the ammonium chloride inside, okay, the ammonium chloride gets into the water, and at the end of the day, the water becomes very cold. Okay, the water becomes very cold. Now, why is this thing happening? This is because, just as I told you, that in this particular reaction, energy is absorbed from the surrounding system. So the energy is absorbed in the surrounding system, and what basically happened that the surrounding system will fall in energy. Okay, there's a fall in temperature of the surrounding because energy has left that particular system and has gone into the product formation. It has gone to form the product. Okay, so basically that's what happened. So at the end of the day, the reaction the system becomes very cold, but the product ends with a higher heat content. So let's look at this particular example here. Okay, when you dissolve sodium chloride in water, this is ammonium chloride. Okay, so ammonium chloride. Now when you pour it in water, that is why there is an aqueous here. Now you can see that first of all, all reactions begin with a minimum supply of energy, and that is called the activation energy. So the energy, first of all, is supplied to the reactant to heat up the system. But basically what happens is that as the heating is taken, as the system or the reactant gains energy, okay, bonds must break. Okay, bonds must break. And so what basically happens is that for the endothermic reaction, there's large amount of energy that is used to break the bonds. And so when you put the ammonium chloride in water, for the ammonium chloride to break down, it has to take more energy from the surrounding. And so the surrounding will have to fall in temperature or have to lose the energy to the bond, okay, breaking process. So for the bond to break this time around in the endothermic process, for the bonds to break, large amount of energy is required to break the bond, and the energy, okay, is absorbed. Okay, the reactant absorb energy from the surrounding, and the surrounding tend up to have a lower heat content. Okay, and all the energy now goes into bond breaking. Okay, so basically the bonds get break. Okay, then the bonds between the atoms, okay, break down, but all the energy that, okay, was supplied to the reactant is now used to break down the bond, and sometimes it pick up a lot of energy from the surrounding. Okay, so this is the free atoms. Okay, this is the free atoms that has been formed from here. Just as I told you that energy goes into the reactant, bonds must break. And so you can see that bonds here are just about to break over here, and they are even broken already, and they are far apart, but because they are interactions, they produce what we call a transition state. Okay, so the energy supplied is used to break down the bond, and in endothermic process, large amount of energy is used to break down the bond. Okay, large amount of energy is used to break down the bond as compared to the energy that is given off during the bond formation. So from here you can see that when ammonium chloride dissolves in water, it gives you the ammonium ion and then the chloride ion. But before this ammonium chloride and then the chloride ion is formed, okay, large amount of energy was required to break down the bonds. Okay, was required to break down the bond, and so all the energy went into bond breaking. Okay, rather than the bond formation. If I told you that in all bond formation, energy is given out. But in the endothermic energy diagram, small amount of energy is given off. Okay, small amount of energy is given off to the surrounding. Small amount of energy is liberated to the surrounding compared to the energy that was required to break down the bond in the reactant. And so when you do your subtraction, you can see that the value here become positive. Okay, the value here become positive. So in endothermic reaction, once again, during the bond formation, after the energy is supplied to the reactant and it goes to break down the bond, all the energy that is supplied to the reactant is used to break down the bond, and the system or the surrounding system fall in temperature because every energy goes to break down the bonds. This time the bonds are very hard to break, so energy goes to break down the bond. Now this time from here, free atoms have been formed. That free atoms interacting produce what we call the transition state, and I've defined what the transition state for. Then basically what happened, these free atoms end up to form the what, the product. Here please look at it. Here, the energy that was released during the formation of the product from the transition state, okay, the energy that was released is smaller than the energy that goes that is used to break down the bonds. Okay, so all energy has been used to break down the bond, but the energy that was given of doing the combination of these atoms, during the combination of this atom, or during the formation of the product, is small as compared to the energy that was used. So if you want to find the enthalpy value for the reaction, I just told you that there is a difference in the enthalpy of the product, okay, and that of the what, the reactant, and that of the reactant, and that of the reactant. So when you put in the values here, you can see from here that for the potential energy value, the reactant is lower as compared to the what, as compared to the product. And so assuming here, because it's lower, let me give it what, 10, and then here let me give it like 15. Okay, let me give it 15. Let me give it 15. So basically what happened, you subtract the 10 away from the what, from the 15, and what are you going to get? At the end of the day, you will get what we call a positive value. You get what we call a positive value. So the positive value, are going to get positive 5. And so in endothermic energy diagram, the enthalpy change is a positive sign, because when you subtract the reactant away from the product, you will get what we call a positive sign. So basically that is what happens in all endothermic reactions. In summary, once again, in all reactions, bond must break. Energy that is supplied is used to break down the bond. In endothermic reaction, large amount of energy is used to break down the bonds rather than the product forming, okay, than that of the product forming. Then when these bonds are broken, because all the energy is used to break down the bond, they are not having that energy, okay, to form the product. And so just small amount of energy is used to what, is liberated as the product is what, is formed, okay, as the product is what, is formed. So basically that is what happened in what, endothermic reaction. Other examples of endothermic reactions are, one, the dissolution of ammonium nitrate, okay, and then the dissolution of what, white anhydrous copper 2 tetraoxosulfate 6. These are all endothermic reactions. I just told you that heating of water is also endothermic process. Heating of water is also endothermic process. So let me tell you that most reactions are exothermic reaction rather than endothermic reaction, because it is a spontaneous process. Exothermic reaction is a natural process rather than the artificial process in the case of endothermic reaction, where energy is what is taken from the what, from the surrounding. So we'll end our lecture here, and in our next episode we'll be looking at each of the standard enthalpy changes, like the formation, standard enthalpy of formation, standard enthalpy of combustion, neutralization. We'll be looking at all these examples. Thank you.